In the last few videos, we learned about correlation analysis that can be used to quantify the strength of association between two variables. In this video, we will learn about linear regression, another useful tool in examining the relationship between two or more variables. Regression analysis is one of the most frequently used tools in the world of finance. It quantifies the relationship between a variable called dependent variable and one or more explanatory variables, all called independent variables. Regression analysis can be handy when we want to forecast a future dependent variable with the help of patterns from our historical data. Let's consider an example. In general, the larger houses are more expensive than the smaller houses. If we want to test the hypothesis that the size of the house predicts prices, we can do so by using a regression analysis. In this case, our regression model will have two variables, the price of a house and its size. The explanatory variable or independent variable is size, as it helps us explain why certain houses cost more, and the dependent variable is price, as it is being explained. So if we know the value of explanatory variable, house size, we can determine the expected value of our dependent variable, house price. There are many other factors that determine house prices. Size is one, but it is not the only one. Impact of all the other factors can be summarized in the error term. If we use only one variable in regression, it is called a simple regression, while regressions with more than one variable are called multiple regression. Let's look at another example. Recall, in the video on correlation analysis, we find the positive association between money supply and inflation. Regression analysis assumes the existence of a linear relationship between the two variables. One straight line is the best fit and can help us describe the relationship between all the data points we see in a plot. How do we determine which is the best fit line that will help us describe the relationship between money supply and inflation? Well, we simply have to find a line that minimizes the error observed between itself and the actual observations. See how different observations tend to deviate? Each deviation from the line is an error, and the best fit line is the one that contains the least error. Going back to the concepts learned in the basic algebra class, the equation of a straight line is given as y equals mx plus b, where m is the slope of the line and b is the y-intercept. Replacing m by beta and b by alpha gives us the regression equation. The epsilon is the error term that summarizes the impact of all other factors in explaining our dependent variable y other than the chosen independent variable or x. Now let's understand how linear regression estimates alpha and beta. The intercept or alpha and the slope beta are chosen so as to minimize the sum of squared vertical distances between observation and the best fit line. With simple math and in a simple regression model which contains only one independent variable, the slope coefficient equals to covariance between the dependent and the independent variable divided by the variance of the independent variable. And the intercept is given as the mean of the dependent variable y bar minus the estimated beta times the mean of the independent variable or x bar. Let's continue our example of predicting inflation based on money supply. Recall, we calculated the covariance and variance for calculating the correlation coefficient in one of the previous videos. We can use the covariance and the variance of the money supply to get an estimate of our slope coefficient or beta as follows. Beta is the ratio of covariance between money supply and inflation and the variance of money supply. This gives us a beta estimate of 0.3327. Using the means of inflation and money supply and the beta estimate, we can calculate the estimate of our intercept or alpha. The estimated intercept or alpha hat is equal to y bar minus the estimate of slope coefficient or beta hat times x bar, which is equal to 0.0320 minus 0.3327 times 0.0973. Solving this equation gives us our estimate for intercept as negative 0.0003. Finally, we plug in the estimates of alpha and beta to get our regression equation, which can be described as follows. Inflation is equal to the estimate of our intercept, or negative 0.0003, plus the beta estimate of 0.3327 times money supply. The intercept term, or alpha, tells us that if the money supply is 0, then our best estimate of inflation is negative 0.0003. The slope term, or beta, tells us that if money supply increases by 1%, the inflation will increase by 0.3327%. We can use the regression equation to estimate the rate of inflation for a given level of money supply. Let's assume our forecasted money supply is 0.13. Then we can use the regression equation to forecast the rate of inflation as the intercept plus the slope coefficient times the money supply of 0.13. This gives us the estimate of inflation as 0.04295. In the next video, we will learn how to distinguish between a good and a bad regression model.